this video, we'll work through a Coulomb's law problem. Now this problem will basically be fairly complex and take you up to an A grade. 4-point charges A, B, C and D are arranged on the corners of a square of sides 25 centimeters each. If A and B each have a charge of positive 1 microcoulomb, while C and D have a charge of positive 2 microcoulombs, what is the resultant force on a charge E of a 1 microcoulomb placed in the centre of the square? Okay, so let's work through the problem. So the first thing we want to do is to write down a diagram. So here's our diagram. There's A, B, C and D all labelled in the square with E in the middle. We know the sides are 25 centimetres, which we can convert to 0.25 metres. We write in our charges from what we know in the question. Now note that 1 micro basically means 1 times 10 to the negative 6. Now this is a vector question because the forces are acting at an angle. Now all of the charges are positively charged as well as E, and as a result they repel. So we can see that E is 1 microcoulomb. So as they're all positive, they're all going to repel. Now basically there is going to be a push from the bottom in an upwards direction from both D and C, as you can see here. There will also be a push downwards by A and B, and these will be both at an angle to the charge E. Now because we're at a square and because the forces are the same, they're all going to be at 45 degrees to E. Alright, now we also know that we can calculate F by using Coulomb's law, which is basically F equals K times Q1 times Q2 all over D squared, where K is going to be our constant, which is 9 times 10 to the 9 Newton meter squared per Coulomb squared. Now from this we can draw a force diagram or a vector diagram. So here's E, and here are the forces that are going to be generated. This one coming from C, this one coming from D, and you can see they're acting upwards. We're also going to have forces acting downwards by B and A. So you can see they're acting at 45 degrees to E in each case. Now note that the arrows are slightly bigger for C and D than B and A, and this is basically because C and D have charges which are going to be double that of B and A due to the forces being double. Okay, so basically now what we're going to look at is we're going to look at how we can calculate D, because D is our unknown at this moment. We know K, we know Q, but we want to find D. Now as it's a square, all of the distances at 45 degrees acting on E are going to be the same because E is in the centre. So we can see here, if we just look at A and B, we know that the distance here is 0.25. We know that the distance down is 0.25. So we can find D, which will be the resultant of these two situations. So what we basically get for D, we're going to have half of 0.25. So there's a typo there, apologies. It should be 0.125 squared plus 0.125 squared, and then it's the square root. This all comes, which is accurate now, to the distance being 0.177 meters. So that is the distance at 45 degrees from A to E, B to E, C to E, and D to E. So now we know the distance, we can now calculate the force. Now the force from A to E is K QA times QE, the charge of A and the charge of E. So it's 9 times 10 to the 9 times the charge of QA times the charge of QE squared. But note that both A and E have the same charges of 1 microcoulomb. So that's why I've got 1 times 10 to the negative 6 all squared. Now we know that the distance, as we calculated earlier, was 0.177. So that means we square that as well. And as a result, the force that will be generated at 45 degrees on E will be 0.29 newtons. Now as charge B is the same as A, it will also be 0.29 newtons. There's no change there, just a different direction. C and D are double the charge of A and B. So as a result, the force will be double the charge. So as a result, we can calculate the force for C being 0.29 times 2, which equals 0.58 newtons, and that will be the same for D because it's the same charge as C. So now we've got our four forces which are acting on E at 45 degrees to the vertical. So if we go back to our vector diagram, basically this is what is going to be produced. Here's E. There's a force acting at 45 degrees in both directions of 0.58 from C and D and 0.29 downwards from B and A. D and B are on the same plane, but they're in opposite directions. As a result, I can take these two away. Let's say that 0.5 is going to be positive, so the opposite direction is negative. So it's 0.58 minus 0.29, which equals positive 0.29. This is exactly the same for C and A. Now the resultant will be a combination of these two forces acting upwards, because they're positive, with a force of 0.29 newtons. So basically we can draw our vector diagram here. Here's our resultant force, and we've got our two forces which applied together produce this resultant force, one from vector D and A, and one from vector C and B, both at 0.29 newtons at 45 degrees. Now, as both are at 45 degrees and they're a square, these two vectors form together to make a right-angled triangle. So we can draw a vector triangle basically made up of these two forces. Our force of resultant will be made up of 0.29 and 0.29 at 45 degrees of each other. As a result, we get a right-angled triangle. So our resultant can be calculated just using Pythagoras. So basically, our resultant will be 0.29 squared plus 0.29 squared, the square root of the whole lot, which basically will end up with a force of 0.49 newtons in an upwards direction. Well, I hope this makes sense. Thanks for watching and join me again.